Hello everyone. Uh, Welcome to the week 3 of the Recommendation System Learning Book Club. Today we'll be talking about how to build a content-based recommendation system using different architecture. So a little bit about me. My name is Rohan Singh Rajput. I'm currently working as a senior machine learning engineer at Headspace. This is my LinkedIn profile if you want to learn more about me. And if you have any doubt and questions, you can always message me on my LinkedIn. So, discussing about today's agenda, uh, the first 5 minutes we'll do a small introduction, a little bit about the book, and in the next 30 minutes, we'll discuss about what are the different learning from the book we have. The remaining 20 minutes we have for the discussion of the learning of the book, and the last 5 minutes we'll just wrap up and discuss about what is the next chapter we'll be discussing in the book chapter. So, little information about this book. The name of this book is Building Recommendation System in Python and JAX. It is written by Bryan, Bischof, and Hector. The reason we chose this book because this is one of the advanced recommend. This is the book with state-of-the-art advanced recommendation system topics. It's a highly practical oriented and it's written by industrial professionals. Uh, so let me start with the chapter 5. The chapter 5 of the book tells about how do we build a content-based recommender system. So as if you joined like previous book chapter, we discussed there are like two types of uh, recommendation system. One is called content-based recommendation, another is called collaborative filtering recommender system. The difference between content-based and collaborative filtering recommender system that you don't need user interaction data for building content-based recommender system, whereas if you are building a collaborative filtering model, you have to have historical user item interaction data. Now, let me start with the uh, some of the discussion about this book. So, this book talks about how can we build a content-based recommendation system using the STL dataset. So, STL dataset is a dataset about clothing and a different product. It's its full form is shock to look up. It's a dataset from Pinterest, and in this particular recommended system, we would like to find out a similar uh, product based on a scene. So what is a scene? Scene is an image that actually help us to identify what are the different aspect of that image. That means that scene can be like someone is you know drinking a coffee, or someone sitting outside, someone sitting in a library, and based on that scene, what type of product you can recommend to that particular user. So in this chapter is pretty much different than the previous chapter because this chapter is more about practical implementation. We'll be discussing lots of codes in this chapter and how to build this content-based recommender system using this STL dataset. So first, like we install all the required packages and libraries, and we start with a random item recommender. So in the random item recommender, you can see that this is the code for the random item recommender. But what does it do? It just fetches like random items from the STL dataset, and you can see like these are like different types of clothing item available in this STL dataset. So how do we do it? Uh, First, so we are using various libraries here. Uh, Mostly it is built on like JSX, TensorFlow, and other Python libraries. Uh, First, we define like file path and number of items required as a flag. Uh, then we also help, like we also like tag what are the, so these actually flags used for command line interface. When you run a Python file, you can actually provide these as an input argument, and these input argument will help you to run this code uh, from your command prompt. So basically you can set up like what are the um, required flag in whenever you give any command. And first method is like how do we read the product catalog. So in this product catalog we will first open the file, and we load all the data set into this result variable, and then we'll return this result variable. Now, what we are doing, that we are generating an HTML called output HTML, which is an .html file, which actually help us to display the recommenders, what we like all the like recommended images, what we will capture from this program. So if we see the main, like we first like read the catalog with input file, and then we convert it to a Python list, and then we randomly shuffle that particular list, and then from that list we will choose the number of items that we want to display on our HTML using this catalog function. So let me use a pen. So as you can see that this particular function will help us to display all the product. As we have seen our previous chapter, that we can always collect that there are three essential components in a recommender system. The first component is called uh, the collector, the second is called the ranker, and third is called the server. So uh, the collector here is just like collect the random samples from the catalog we can see here, right? And it uh, it our ranker, our ranker will just we don't have any ranker because we are just randomly our uh, output. So here we are just selecting a random items from the catalog, and in the server we actually put a cap that how what is the maximum number of content we need as an output, right? So once we put all of this thing here, it will generate an HTML file, and you can open that HTML file into any browser, and in the browser you will see that this is the output it will generate. So this is a very simple recommender system, because here we are not doing any kind of personalization, we are just randomly sampling our data set. But now we will see that how we can make a more sophisticated model using uh, uh, some neural network architecture. So when in this particular case, because we are dealing with images, right? We would like to use like convolution neural network to build this model. Convolution neural network, if you don't know more about it, it's a neural network that actually utilize image data set, and it has like layers of several layers of network that actually reduce the image higher dimension into like lower dimension, right? So it actually generate this compact embedding, where you will take like a 3D image, right? uh, 3D image or three channel image, and co- convert that image embedding using a neural network into like a linear compact embedding. Now, why are we using CNN? Because these are like image vectors. And second thing, we don't want to just we want to learn from the internal representation of the image rather than just relying on the color values. Because if we rely on the color value, if we see most of the images have like background information, like the most of the images are covered with the background color, and it will start like biasing towards those background color rather than the actual content of the image. So that's why we are using a CNN here. So in this, we have like a embedding vector, which is a feature vector for the image from data in fixed size. As I said, like all these images can be represented using like a numerical representation, and using any kind of color code mechanism, we can actually convert these images into a dense single dimension uh, vector, which is known as embedding. These embedding are also known as feature vector because these actually incorporate all the features of the image. Now, in this particular program, we also use like bash norm to reduce internal covariance shift. It's a pretty common technique used in many neural network architecture. uh, One more thing we have to see that like in this particular CNN, we are using ResNet architecture. So ResNet is a more advanced form of uh, neural network. If you want to learn more about it, please read the ResNet paper, which can give you more information. Uh, it has like lots of bypassing layers that can help you to quickly learn more detailed information about the image. The code is written in JAX, FLAX, and Optex libraries. So these three libraries are primarily uh, deep learning library that can help you to first, like JAX can help you to optimize your code. FLAX help you to build like these neural networks with higher level of abstraction, and Optex can use for like hyperparameter optimization. The most important thing here that we have to define our loss function. Now, why do we need loss function? Because without any loss function, we cannot know that like whether uh, our recommendations are good or not. And for that, like we have created this loss function that actually takes three things. First, it takes the input image. So this is the input image. We also call it a scene. So what we are doing based on a scene, we are recommending product, right? So I will explain you more in more detail. So suppose in this particular scene, like scene number one, you have product one, product two, product three, right? So suppose a person is sitting on a coffee table outside. What type of garment you want to recommend that person, right? So the person sitting on a coffee table will be our scene, and you know different pair of pants, shirts, or shoes can be our product. So how do we do that? Like first we send our input image to our loss function. We define what is a product, positive product. So positive product can be our like training data set, what we train from the what we train our model from the historical data set, and the negative product is the random sampling data set, which does not resemble with the output, right? So we'll go more detail in chapter 12 about why uh, uh, negative sampling is required here, but just the basic idea is that you just sample some of the uh, images from your data set and randomly give them as a negative rating, and based on this thing we define our loss function, which is a maximum of 1 plus score seen product negative, score seen positive. And this can be like some kind of score here could be any kind of like dot product or some kind of cosine product, cosine score that can help us to find out how close these two are. So if we see that there should be a higher gap between positive and like seen and negative gap, so it should be like some kind of negative relationship between seen and negative product, and there should be some kind of positive relationship between seen and uh, product, right? Okay, and please do watch the previous lecture if you want to learn more about how do we calculate these scores. So this is the program. First, like just we'll try to break it down. So here we are building like a TensorFlow input data pipeline. In this particular data pipeline, we have like defined several functions. So this is a normalizing image function. Why we do it that? Because the images can have like different sizes. It's good to like normalize them to better performance of the model. Second, like processing image, the process image actually takes an input file and decodes into like a into a channel, decode based on that channel into a vector, and then we can actually resize that vector or tensor into required format, and then we normalize this image. So normalization function, nothing that we did on the top, and then we return this particular image. uh, Again, this is just like process image with id. So we want to this is kind of an hash function. This actually help us to maintain the id and image information. uh, Process triplet in this particular, that because we have like three images, so we just want to keep we want to apply the operation for all these three images, and then we have create data set where we just taking three input files, right? So as I said, like we need a scene, we need a positive product, and we need a negative product. And once we take that triplet, we actually pass it to this tensor pipeline, and then we apply this process image operation on this on all of these three images. So this is the this is the architecture we have. This is the model. So this is entire our model. As we can see, we need an CNN, but so this vanilla CNN we have that actually help us to generate those embedding for us. So as you can see, we are using this NN compact, which actually help us to initialize all the uh, parameters that required, and this all can be done using this flax library. The flax library can help you to uh, boot load all those information. So in this particular call function, we have this input x, and then we have a boolean which is a train. Here we want to identify whether we are training a model or not. So first we generate a residual, then we generate a first layer as an nn con. This is just generate like in like a based on like different filters. So in this filters, it actually generate uh, all the network architecture. Here we can see that we are applying bash norm to the layer, and then we are using this squish activation function. Then again, we apply the second layer. We again apply the squish function, and then we in the final layer we actually uh, expand our uh, the multi-dimensional array into single dimensional array as an output. Here we can also see that we are using like average pooling. Average pooling is a method of like how do we want to like convert those like three dimension into a like higher dimension into lower dimension. So rather than there are various techniques are there. One of them is like max pooling or average pooling. So in the average pooling, we take average of this entire thing and just shift it to into one particular cell, right? Uh, so now once we defined our vanilla CNN, we can use this vanilla CNN to build our STL model. So in the STL model, what we are doing, we are creating two type of towers, right? So there is a tower number one and there is a tower number two. Don't confuse with the two tower model, but here just we are using CNN for because we have like two types of images. One is called scene and another is called product. And for that, like we need like two different towers of CNN. So what we will do, we will first again there are different methods we have defined here. So as you can see that like we define a default filter of 16, 32, 64, 128. uh, in this particular filter, we actually first like we create this scene CNN tower. So again, like we already defined our CNN class there, and based on that we can uh, generate our scene CNN tower. Similarly, we can generate our product CNN tower. We can get like what is the embedding of the C in CNN and what is the embedding of the product CNN. Uh, Again, in this particular call function, what we will do, we will try to generate uh, scores of different uh, embeddings we have. So in the scene embedding, first we generate a scene embedding, then we'll generate a positive product embedding where we just uh, introduce like a all the training data, so that our training data actually can help us to generate the positive product embedding. And as I said, like we are just using a random sample data to generate our negative training embeddings. In the negative training embedding, we will just try to generate uh, negative product embedding. So these are just randomly sampled images for particular scene. And once we have all this information, we can actually return this positive score, negative score, and all the different embeddings. Uh, Again, for this particular training pipeline, so this is just a model architecture we have, but in the training pipeline, what we'll do, like we'll first generate like different positive and negative triplets. So what we will do, we will you will be using these different way. First, basically, what we want to do, we want to have like a some kind of random number generator that required to generate a negative uh, embedding. And for negative embedding, we are using this JAX random PRNG key. The thing is that this is a functional key. So what do you have to remember, that you have to use this random split key always to preserve the state of the random number. Otherwise, it will not work in JXX. And you will generate your training and testing example based on the data you have. So uh, you also need in this particular program, you have a test embedding, and then you have like a training embedding. What you do, you train your model first, and then you test on this test data set. And you want to apply like similar operation on both test and train data set, and that's why you have to have this random key split in your negative indices. Uh, so here we are just string shuffle, right? Okay, so what does it do? Like it will just like shuffle the array, and yeah, it's just like shuffling the array here. Let me see here what it's doing. Okay, yeah, I think it's just shuffling the array using this random keys state. Okay, so now once we do that, we have our like training and evaluation steps where we generate like a different score. And for that, we have to define our loss function. In this particular loss function, we need like the state of the training data set, uh, the scene, the product, positive product, negative product, the regularization, and batch size. So what it does, it actually apply like all the operations into onto our like our state. And in this particular state, what we do, like we try to generate this regularization loss function for our triplet. And why we do this regularization loss? Because sometimes, like if our model get overfitted, then it should actually reduce those different uh, weights of the weights of the our model to uh, overcome those overfitting problem. And for that, like we use like this regularization technique here. And also because we are using uh, stochastic gradient descent, we have to have this gradient function with us. That gradient function is actually help us to uh, we will like to have a applied derivative operator on our loss function. And once we apply derivative operation on loss function, like we want to preserve those state in those gradients, and that can help us to generate a new state and loss. So as you can see that JAX is a little bit a functional programming language. That's why we have to like preserve the state, and every time we generate a new state and loss function based on the previous state we have. And similarly, we have the evaluation step where we use our ad- evaluation data to uh, to generate the triplet loss, what we similarly did for the train step. Now this is the final program that combines all of that. The first, we set learning rate, regularization test, and output size. And once we do that, we actually initialize. So here we are running it into weight and biases uh, platform. What does weight and biases platform do? It actually help you to do this hyperparameter tuning, and also can help you to monitor your model weights and as they bias weights and the different parameters to see that like how your parameters or how your model is optimizing. Currently, we are running it on a GPU device. We start the eager execution. In the eager execution mode, that it actually help us to run your TensorFlow as a, let's say, in a eager evaluation. That means more Python-like feature. Uh, then we log all this information into image directory, and then uh, we would like to get all those images. So this is the entire program. So first we set up all those our input parameter, then we generate our like test and train data, then we define like a number of train data and test data. Here we shuffle the train data set to generate test and train uh, uh, input data, and using that input data we actually run our program into various iteration to generate the output. So if you run this program, what you'll do, like you will actually start getting you'll start training our model, and try it will also use uh, weight and biases to actually give you the monitoring of the model. uh, as you can see that you can actually um, uh, export your model to a weight and biases platform. And here we are using the Adam optimizer from Optex that can help us to optimize our training data set. Uh, Again, all of this thing will be exported to the weight and biases platform. And on the weight and biases platform, you can actually uh, help you can actually see the output of the model. Uh, okay. As and once it completes, you actually save this all information into uh, as a Pinterest dot model file as in on like your weight and biases platform. So this is the output. In this particular output, we see the evaluation loss, which is going down. Uh, we we can also see that what is the different learning rate we have, what is the different regularization technique we have, and what is the runtime and output size. Once we complete that, we can actually use uh, our top K recommendations uh, to generate the output. In this, we have different output vectors. That means we open our model, we serialize our model set, and then we actually output this data set as an TensorFlow data set. model. And once we complete that, we can actually save it into a file. So once we do that, we have all the top K uh, scene embedding, and using in this top K, we can actually find out uh, all the important nearest neighbor, and these are the like nearest neighbor of the output, and this is the another one. So thank you for the discussion, and yeah, we'll see you next time.